Welcome to Module 5, Psychrometrics and Moist Air. In building automation, temperature is only half of the air conditioning story. Moisture is the other half. Two spaces can both read 72 degrees, but one can feel comfortable while the other feels sticky, dry, or at risk for condensation. In this module, we will connect moist air science to BAS decisions. What to trend, what to verify, when to trust a humidity value, and when the data is warning us that the sequence is missing the real problem. As we go through the module, keep one field question in mind. Before I adjust a set point, do I understand what the air is doing? By the end, you should be able to look at humidity complaints, economizer operation, cooling coil performance, and dew point protection with a stronger engineering mindset. Let's define what success looks like for this module. You are not here just to memorize dry bulb, wet bulb, dew point, relative humidity, humidity ratio, and enthalpy. You are here to use those values in real BAS decisions. After this module, you should be able to explain what each moist air property means, recognize common psychrometric processes, and understand why humidity data can be misleading if it is viewed by itself. You should also be able to connect psychrometrics to coil control, supply air reset, economizer limits, condensation alarms, and troubleshooting. In the field, this helps you avoid the common mistake of treating every humidity issue like a thermostat issue. Moisture has its own story, and the BAS professional must learn how to read it.
Here is the roadmap for the module. We will start with the basic idea that air is a mixture of dry air and water vapor. Then we will separate the main properties: dry bulb temperature, relative humidity, humidity ratio, dew point, wet bulb temperature, and enthalpy. After that, we will use the psychrometric chart as a map. We will look at heating, cooling, humidification, dehumidification, evaporative cooling, and air mixing. Then we will apply the ideas to real BAS work: mixed air verification, cooling coil dehumidification, condensation protection, and a high humidity VAV scenario. The goal is practical. When a building feels humid, when a cold pipe sweats, or when an economizer brings in outdoor air that looks good by temperature but bad by moisture, you should know what to check next. Air is a mixture. That sounds simple, but it changes how we troubleshoot buildings. Dry air carries sensible heat and supports ventilation. Water vapor carries moisture and latent energy. The BAS sees sensors and trends, but the professional has to connect those values to what is physically happening in the airstream. Think about two rooms at the same 72-degree dry bulb temperature. One room may be at a comfortable humidity level. The other may be humid enough that occupants feel sticky, paper curls, cold diffusers sweat, or mold risk increases. The temperature value alone does not tell the complete story. In BAS work, Psychrometrics helps us move from a simple question, what is the temperature, to a better question, what is the condition of the air? These 6 properties are the core language of moist air. Dry bulb temperature is the ordinary air temperature and the value most BAS graphics show first. Relative humidity is the percent of saturation at the current temperature, but it is not the actual amount of moisture by itself. Humidity ratio tells us the mass of water vapor compared with dry air. Dew point tells us the temperature where condensation begins. Wet bulb temperature helps us understand evaporative cooling potential, especially for cooling towers. Enthalpy combines sensible and latent energy, so we can compare total air energy, not just temperature. Here is the field rule. Do not make a humidity decision from dry bulb temperature alone. Always ask what the moisture is doing.
The psychrometric chart can look intimidating at first, but it is simply a map of air temperature, moisture, and energy. The horizontal axis is dry bulb temperature. The vertical axis is humidity ratio. The curved lines show relative humidity. The saturation curve is where the air is holding as much moisture as it can at that temperature. Dew point is read along that saturation boundary. Wet bulb and enthalpy lines run diagonally. For BAS troubleshooting, the chart helps you see direction. Heating moves the air to the right. Sensible cooling moves it left. Dehumidification moves it down as moisture is removed. Mixing falls between two air streams. Once you can see the path, you can ask whether the system is doing what the sequence says it should do.
Relative humidity is useful, but it is also one of the most misunderstood BAS values. Relative humidity changes when temperature changes, even if the actual moisture amount stays nearly the same. If air is cooled without removing moisture, the relative humidity rises because cooler air has less moisture holding capacity. If air is heated without adding moisture, the relative humidity falls because warmer air can hold more moisture. So a low indoor RH in winter does not necessarily mean moisture was removed inside the building. It may simply mean cold outdoor air was heated. This is why we interpret relative humidity together with dry bulb temperature, dew point, and when needed, humidity ratio. RH alone is not enough evidence for a professional decision. Dew point is one of the most practical values in building automation. It tells us when condensation can begin. If the surface temperature of a pipe, duct, chilled beam, or radiant panel falls below the air dew point, moisture can condense on that surface. For example, if room dew point is 58 degrees and a radiant surface is 55 degrees, the surface is below dew point. That is a risk condition. The control sequence may need to raise the water temperature, reduce room moisture, lock out cooling, or maintain a safety margin. But remember, dew point protection is only as good as the humidity sensor, temperature sensor, location, calibration, and local air conditions. Do not protect a critical surface using a bad or poorly located measurement. Wet bulb temperature and enthalpy are especially important when we evaluate outdoor air and total cooling load. Wet bulb temperature tells us how much evaporative cooling potential exists. That is why it matters for cooling towers and evaporative cooling systems. Enthalpy is different. It combines sensible and latent energy. This becomes very important for economizer logic. Outdoor air may be cooler than return air by dry bulb temperature, but if it is very humid, it can still contain more total energy. A temperature-only economizer may save compressor energy in one condition and create humidity or latent load problems in another. A good BAS decision looks at the property that matches the risk. For total energy, think enthalpy. For condensation risk, think dew point. Every common HVAC process moves air in a recognizable direction. Sensible heating raises dry bulb temperature while humidity ratio stays nearly constant. Sensible cooling lowers dry bulb temperature until the air reaches the dew point. Once the coil surface is cold enough and moisture begins to condense, the process becomes cooling and dehumidification. Humidification adds moisture. Evaporative cooling lowers dry bulb temperature while increasing humidity ratio. Mixing combines two air streams, and the mixed condition should land between the outdoor and return air conditions based on the airflow proportions. In the field, before adjusting logic, ask, what process is this equipment supposed to perform right now? If the measured path does not match the expected process, investigate before changing set points. Mixed air should make physical sense. If an air handler mixes outdoor air and return air, the mixed condition should fall between those two airstreams. When moisture and total energy matter, humidity ratio or enthalpy is usually better than dry bulb temperature alone. For example, if outdoor air is 20% and return air is 80% by dry air mass, the mixed enthalpy should be a weighted value between the two. If the BAS mixed air sensor reports something far outside that expected range, do not immediately blame the dampers. Check airflow fraction, sensor location, stratification, calibration, and whether the air is actually mixed at the sensor. A single mixed air sensor in a stratified airstream can tell a very convincing lie. A cooling coil does not automatically remove moisture just because cooling is enabled. A coil removes moisture only when part of the coil's surface is below the entering air dew point. That depends on entering air conditions, chilled water or refrigerant temperature, airflow, contact time, coil selection, bypass factor, cleanliness, and condensate drainage. This is why a VAV building can satisfy temperature and still feel humid. If airflow is low and supply air reset raises the coil leaving temperature, the coil may not remove enough latent load. Lowering room set points may hide the symptom, but it may not fix the moisture problem. A better response is to look at coil leaving condition, airflow, dew point, reheat, ventilation, and reset logic together. Let's apply this to a common field scenario. The building temperature is near set point, but occupants say the air feels sticky. The trends show rising relative humidity in summer. Cooling calls are light, VAV airflow is reduced, and the air handler has reset supply air temperature upward. The hidden issue is that the system is meeting sensible load but not removing enough latent load. The coil is not being kept cold enough, or the air is not spending enough time at the coil to dehumidify effectively. The professional response is not to randomly lower space temperature. The response is to trend dew point, coil leaving air temperature, airflow, outdoor air moisture, reheat, and reset behavior. Here is the question for the learner. What would you verify before changing any set point? Most psychrometric failures are not caused by one bad set point. They usually involve measurement, sequence, air balance, outdoor air, infiltration, or coil behavior. Common mistakes include treating relative humidity as absolute moisture content, ignoring dew point for cold surfaces, using dry bulb economizer logic in a humid climate, resetting supply air temperature without checking dehumidification, and trusting a mixed air sensor located in a stratified airstream. The field checklist is your protection. Trend dry bulb, relative humidity, and dew point. Verify humidity sensors. Evaluate outdoor air moisture and infiltration. Trend coil leaving condition and airflow. Compare cold surfaces to dew point. This is how you move from complaint to evidence. Let's pause for a knowledge check. First, why can relative humidity rise when air is cooled? Because the air's saturation capacity decreases as temperature falls, even if no moisture is added. Second, what is the best variable for condensation risk? Dew point compared with surface temperature. If the surface is below dew point, condensation risk exists. Third, why can a mixed air sensor mislead the BAS? Because outdoor and return air may not be fully mixed where the sensor is installed. Stratification can make one sensor read only part of the airstream. These are simple questions, but they protect real systems from bad troubleshooting. For the assignment, choose an AHU or VAV system and use Psychrometrics to explain what the system is doing. Trend dry bulb temperature, relative humidity, dew point, outdoor air condition, supply air temperature, and coil leaving condition. Then identify the active process. Is the system heating, cooling, dehumidifying, humidifying, mixing, or doing more than one at the same time? Your recommendation should be based on evidence. Explain whether humidity control is being protected or compromised. Identify the weakest measurement, and propose one safe next test or sequence review. The key takeaway is this: temperature tells only part of the story. Moisture determines comfort, condensation risk, coil behavior, and many BAS decisions. Next, we will build on this by studying airflow, pressure, and air distribution.